Welcome to this video on Hamming tree. My name is Saeed Kargar from University of California, Santa Cruz. This is joint work with Faisal Nawab, my advisor, and this work is done by the EdgeLab UCSC that recently moved to UCI. DRAMs have been around for a long time. They are very fast, but their capacity can be very costly, and more importantly, they are not persistent. The emergence of non-volatile memory technologies has changed the landscape of memory systems significantly. They allow us to combine both storage and memory into one device as a hybrid memory. They come in much higher capacities than traditional DRAM. They are cheaper than DRAM, faster than NAND technology, and more importantly, they are non-volatile. So, because of these advantages, a lot of indexing data structures and key value stores are built on NVMs. However, they are not the same. It means that we cannot treat NVMs like DRAMs because they have different properties. Like every other technology, they have their own limitations. First of all, they have lower write endurance compared to DRAM. Second, their write latency is higher than DRAM. And finally, their write power consumption is much higher than that for DRAM. So, if we want to implement the same data structures and key value stores on both NVM and DRAM, NVMs are going to wear out sooner because their write endurance is lower than DRAM. Recently, there has been a growing interest in making key value stores faster and faster by using NVMs. However, because NVMs are treated like DRAM, these systems impose some costs upon systems. But the thing is that, do we really need that much speed when most real-world applications do not or cannot even use that much speed? You cannot drive a Ferrari at its top speed on the city because there are always speed limits. So here we are looking for making systems more efficient while delivering a reasonable speed that satisfies the needs for most of the real-world applications. What we want to design here is the peruse of the key value stores. Here we observe that writing a data item in different locations of NVM is going to cost differently. So we say that if we can monitor these available addresses, we can find the places that cost less for each item. Actually, in another work, we have explored the ways that this problem can be handled using machine learning. But in this work, we approach the problem in a different angle that even costs less than using machine learning. In this method, we built an auxiliary tree-based data structure such as B-tree to organize the free NVM memory locations based on their Hamming distance. So if we want to write an item on NVM using this method, it needs to go through this Hamming tree, and through this Hamming tree, it can find the best place to be written on NVM. By using this, we can increase the write endurance and decrease the power consumption significantly. Hamming tree can be augmented with existing database systems to improve the write endurance of NVMs. So if you want to know more, get in touch with us. Thanks.